Young's double slit experiment. Let us consider a source of light S that emits a light which falls on S1 and S2 placed at d distance apart. Let the light from S1 and S2 produces a interference fringe at the screen mm' at point P. In order to explain the Young's double slit experiment, what I'm going to do, I'm going to use this information to draw a picture. So here is my picture where you can see S is the source, which is basically the primary source. When the source S emits the light, that light approaches to S1 and S2, and S1 and S2 are d distance apart, and the light from S1 and S2, they meet at point P on the screen mm'. Now let's connect the point S with point O, so then this will be my x-axis, and let the point P is x distance from point O, and the distance between S1 and S2 is d. Now the distance of source S1 and S2 from the screen mm' is capital D. Then S2P minus S1P is equal to n lambda. Let this is our equation number 1, where n is equal to 0, 1, 2, 3, 4 dash dash dash, and lambda is the wavelength of the wave. Now what I want to do, I want to find the value of S1P. In order to find the value of S1P, what I'm going to do, I'm going to drop a perpendicular from S1 to the screen mm', and if I do that, I will get a right triangle. This is basically the right triangle, and this is my hypotenuse S1P. So if you look at the picture, point P is x distance from O, and S1 and S2 are d distance apart. So basically S1 will be d over 2 distance from this line, and S2 will also be d over 2 distance from this line. So basically this distance is right here is d over 2, and if I subtract d over 2 from x, we will get this distance. So if I use the Pythagorean theorem, I will write S1P square is equal to this distance, which is capital D square, plus x minus d over 2 whole square, which is this distance. So we will write S1P whole square is capital D square plus x minus d over 2 whole square. In the same way, if we drop a perpendicular from S2 to screen mm', we will draw this line right here, and again we will get a right triangle. This distance from P to O is x, and this distance is d over 2. So this whole distance is basically x plus d over 2. So we will find the distance S2P, and the S2P will be S2P square is equal to d square plus x plus d over 2 whole square. Now let's find the difference between these two equations, and if we do that, we will write S2P square minus S1P square is equal to d plus x plus d over 2 whole square, which is over here, minus d plus x minus d over 2 whole square, which is over here. If we simplify further, we will get S2P square minus S1P square is equal to 2xd. Now let's simplify this equation, and if we do that, we will write S2P plus S1P times S2P minus S1P is equal to 2xd, because I'm using a formula a square minus b square is equal to a minus b times a plus b, and that's how we got this expression. Now we want to find the value of S2P minus S1P, and if we do that, we will get S2P minus S1P is equal to 2xd over S2P plus S1P. For small d is very less than capital D, we have S2P plus S1P is equal to 2d. Now let's substitute the value over here, and if we do that, we will get S2P minus S1P is equal to 2xd over 2 capital D, because S2P plus S1P is 2d from here. If we simplify further, we will have S2P minus S1P is equal to xd over capital D, and let this is our equation 2. So from equation 1 and 2, we have xd over capital D is equal to n over lambda. Now if we want to find the value of x, we will get x is equal to n lambda d over small d. This x is basically for n, so we can also write xn is equal to n lambda capital D over small d. Now since xn is equal to n lambda d over capital D, what we are going to do, we are going to find the two cases. So our first case is constructive interference, it gives us the bright region on the screen, and the bright region is xn is equal to n lambda d over small d, where n is equal to 0, plus minus 1, plus minus 2, plus minus 3, dash dash dash, keep going. Now the second case is destructive interference. It gives us a dark region on the screen, and that is given as xn plus 1 is equal to n plus 1 lambda capital D over small d, where n is equal to 0, plus minus 1, plus minus 2, plus minus 3, plus minus 4, dash dash dash. Now the next thing we want to find the bandwidth. So the bandwidth is defined as the distance between two consecutive bright and dark fringes is known as bandwidth. Bandwidth is denoted by beta, and the beta is equal to xn plus 1 minus xn. Now let's substitute the value of xn plus 1 and xn from here and here, and if we do that, we will write beta is equal to n plus 1 lambda d over d minus n lambda capital D over d. If we simplify, we will get b is equal to lambda capital D over small d, and this is basically the width of the band, and this is how we will define the Young's double slit experiment.